Y13 time again. Polyesters, polyamides. It's one of those little video things where it's just about making sure you understand. So it's probably stop, start, notes, start me back up again, leave me freeze framed in a funny pose. You know those ones on the front of these videos. Just want to remind you first of all, esters and secondary amides. Just what you do to form them. Now the standard way of forming an ester is that. Requires a H+ catalyst, but carboxylic acid with an alcohol will form the ester. If you have a phenol, that won't work. If you have a phenol instead of an alcohol, you're going to need a reactive derivative of a carboxylic acid. And if you don't know what that is, I'll tell you. It's either an azyl chloride or acid anhydride. So things like ethanoic anhydride and ethanol chloride will be examples of the two reactive types. Secondary amide, well, got to be an amine, and this time it's either those two things I just mentioned. So that will produce a secondary amide. When we're talking polyester and polyamide, it's that. Now, we will say something else different a little later, but as a starting point, we need to consider those two there. The polymerization part, these are the three essential things. So it's a condensation reaction. That means a small molecule is ejected as you form the link that you're trying to make. That's either water or HCl. That's kind of the list really. In order to do condensation polymerization, the monomers are different. There are a pair of monomers, two monomers, than they are not the same, although occasionally there was a special case. We'll cover that a little later as well. Well, you'll get that in a question actually, sorry. And the really essential feature is that each of the two monomers is a di-functional group compound. So the functional group will be in the molecule twice. You usually find the functional group, it says their terminal position, that means on opposite ends of the molecule, so as far apart as possible. So if you had 6 carbons, it would be on carbon 1 and carbon 6. So it's that dualing of the functional group that allows you to form the link and then form the link at the other end of the molecule, and so the chain can grow. Hundreds of thousands long if it's a standard size polymer. And so we're going to move on to some drawing on the board, and I'll see you in a moment. Polyester first. Now the example that you, well, mostly see, I'm sure there were lots of polyesters, but this is the one you always see, is PET. PET is a horrific name. Polyethylene terephthalate. PET. Ethylene is an old-fashioned name. It should really be polyethylene. It never gets used. And terephthalate, old-fashioned name again. These are the chemicals that you need to do it. Firstly, it's never seen any ethylene. Ethylene is the old name for ethene, so it's never seen any ethene because the two molecules are, there is ethane 1,2-diol. It's not ethene at all. And this is a dicarboxylic acid. This goes under the name of terephthalic acid. old-fashioned name. It's benzene 1,4-dicarboxylic acid. So they will react together providing you get a catalyst involved. The catalyst they use is this one here, Sb2O3, antimony oxide. It allows you to get very long chains, longer chains. And the standard way of representing a polymer, which is the same at GCSE, is you trap it between square brackets as a repeating unit. So here's the benzene dicarboxylic acid, here's the remnants of the diol. I know why the name is polyethylene or polyethylene, because it talks about this bit here, because CH2 is nominally ethene. And so you have that repeating unit endlessly. Quite good for little cross links as well, because of the polarity of the carbonyl and the oxygen that's somewhere else on the chain. You'll get some dipole attractions. What happens if a polyester comes into contact with these? Well, it's not such an issue for PET in a bottle, but when you have polyester in clothing, which I presume is not quite the same, you find that long-term exposure to acid and you will get hydrolysis. Like you would of an ester, which is the basis of esters forming and then unforming in an equilibrium. If you put them in contact with alkali, it's a much quicker hydrolysis, still hydrolysis, but it's me not writing and talking. Hydrolysis breaks up the ester link, but if you get alkali in contact with polyester, it's a much quicker reaction, and if you're not very quick about getting it off polyester clothes, you'll end up with a hole. So there we are, polyesters. Key feature, each monomer has two of the same functional group. It's dual functional group, dual functional group. You could replace the H's with Cl's and have a dioil structure, and that would also form the polyester. We're going to look at some polyamides. See you in a moment. Nylon is an example of polyamide. Here's a nylon formation. Again, same feature, dual functional groups, amine on both ends of this molecule. I suppose it doesn't have to be on the end, but it usually is on the end. And here's a dichloride, and both of them have got 6 carbons. It's 4 in the centre, CH2 with the NH2 attached. I've shortened it when I get down there, but there, and here there is the 2 with the dioil and then the CH2 times 4 in the middle. So you remove HCl, here's HCl. I didn't say that last time, that you remove water. You remove water when you make the polyester. If you know your mechanism for esterification, you'll know the oxygen from the alcohol stays in the ester, and the OH group of the carboxylic acid leaves with the hydrogen of the alcohol or the phenol. Here's the HCl being removed, and we form the link. Here it is. This here is going to have an N there. That's that equivalent N on the next pair. So the correct way to write that is without the N. And obviously it's N times. Now this would be, like I said, an example of nylon, one of the earlier synthetic materials, with all sorts of sad stories attached to it. But this would be what is termed a nylon 6,6, not nylon 66, 6,6, because each monomer has 6 carbons. And that's where that name comes from. We'll have a little look at one slightly more, not massively more, but slightly more modern polyamide, which is kevlar. That's kind of it really. I'll see you in a moment. So kevlar. Stephanie Kwolek, I think, was the lady who invented the material Kevlar, responsible for an awful lot of life-saving crash helmets, body armour in the military and police. Fantastic material, all down to its chemistry. Those are the two monomers. Again, the dual functional group feature in both monomers, both with a benzene ring in the centre, both 1,4 structures as well. And of course, as it's a polyamide, there's the kick out of the small molecule, HCl. Kevlar has a interesting structure, but I want you to draw what the repeating unit is, with just one of each monomer in it. And I'll get you to pause the video to do it, and when you unpause it, we'll move on to me having the structure on the board. So I'd like you to pause me right now. Okay, so having unpaused me, this is the structure that I was expecting you to draw. Ooh, contribution from the object of the day. And I wasn't expecting this bit down here. I'll come to that bit in a second. So this is the repeating bit up to here that I was expecting you to draw, with the end, with the lines go through the square brackets. So it has the two different monomers joined together. The link onto the next pair goes through there and goes off through there. The thing about Kevlar that makes it so miraculously good at what it does, which is absorbing impact, is the way it's bonded between one line of monomers and the next line. You get a hydrogen bond formed by the oxygen of the carbonyl onto the hydrogen of the nitrogen, and then this is so big that it has instantaneous dipole induced dipole between the rings as well, and it makes it a really solid sort of structure. And you get Kevlar being able to absorb on a molecular scale impact, and so you have this lining up of the chains. But that's kind of it, really. There is a way of producing polyamides, which I've said that you do it with this. There will be an expensive way of doing it. Things with azyl chloride, diol chloride, are notoriously expensive. So one of the ways round that is an alternative way to do it, where you just use the carboxylic acid. You use the carboxylic acid in the amide and you let them react, but they don't react together. And then you heat them up, and having formed a salt, it then decomposes and forms the nylon, well, not the nylon structure. Well, you could form a nylon structure that way, but that is how they make nylon. Or you could form the Kevlar structure. And so there's this alternative route involving some thermally heating, but you do it under an atmosphere of nitrogen to stop it reacting in other ways, because nitrogen being inert, if you've realised that nitrogen is not particularly reactive, that's because it's got a triple bond with a huge energy to split it apart. So that's it, really. That's all we're trying to get across in these. There is no follow-up set of questions. It's just about, have you got the notes straight, really? And that's it. I'll see you for another video very soon. Ta-da!